All right, today we are diving headfirst into a place where the ground under your feet is a constant deadly threat. We're going to explore how some really cutting-edge tech is being used to try and predict a natural disaster. And here's the kicker. The tools being used are available to pretty much anyone. So how does it all work? Let's find out. Okay, so to really get a grip on this challenge, you have to understand the geography of Nepal. I mean, we're talking about one of the most vertically extreme places on the entire planet. The elevation changes are just staggering. So you can imagine when those heavy monsoon rains hit, that dramatic sloping terrain becomes incredibly unstable. The result? Absolutely catastrophic. We're talking thousands of landslides ripping across the country in a single season. So the goal here, and this is a really key point, it isn't about predicting exactly when a landslide is going to happen, down to the day or hour. That's a whole other beast. This is about predicting where they're most likely to happen. It's a concept called landslide susceptibility. You're basically trying to identify the danger zones, the places with the highest probability of failure, all based on what the terrain itself looks like. All right, here's a quick look at our roadmap for this explainer. First, we'll tackle Nepal's unstable ground, then look at the digital toolkit they used. After that, we'll get into mapping the danger and a shocking real-world test. And finally, we'll cover the promise and pitfalls and what the road ahead looks like. Let's jump in. First up, Nepal's unstable ground. And here's the central problem, which is kind of mind-blowing when you think about it. For a country that is so incredibly vulnerable to landslides, there's never been a single comprehensive nationwide risk map to guide things like where to build or where to evacuate. A huge critical gap. So this research, which was led by a Nepali student named Siri Zahal, started by looking backwards into the past. You see all these black dots on the map? Each one represents a known landslide that was triggered by rainfall. That data comes from a global catalog that NASA actually maintains. And the fundamental idea here is, well, it's pretty simple and elegant, really. If we can figure out the exact terrain characteristics of all the places where landslides have happened, we can then go looking for other places that look exactly the same. Okay, section 2, the digital toolkit. Now, you might be wondering, how on earth do you analyze an entire country's terrain? I mean, that sounds like a job for a massive supercomputer, right? Well, yeah. But the brilliant solution here was to use AI and the cloud, which makes this kind of power accessible to basically anyone. The AI at the heart of this whole thing is called a random forest model. And honestly, the best way to think about it is like a super smart detective. It looks at all the evidence, all the data from past landslide sites, and it doesn't just look at it once. It builds hundreds of different decision trees, which are like different lines of inquiry, to figure out the key combination of clues that almost always leads to a landslide. And this is the real game changer. This is what makes it all possible. Google Earth Engine. You can basically think of it as a supercomputer for the entire planet that you can access from the cloud. This is the platform that lets a single student, with just an internet connection, run an analysis on a national scale. I mean, something like this would have been completely impossible just a decade ago. It's a huge deal. It totally democratizes this kind of life-saving research. All right, section 3, mapping the danger. So we've got the historical data, and we've got the digital tools. Now let's dig into how the model actually builds what you could call its recipe for disaster. It's a pretty straightforward 4-step process. First, you gather the locations of past landslides, but also, importantly, places where landslides haven't happened for comparison. Second, you feed the model a whole menu of potential ingredients, things like the steepness of a slope or how much it rains. Third, you just let the AI go to work, training itself to spot the difference between a safe spot and a danger zone. And finally, step 4, you use that newly trained model to generate the risk map for the entire country. And after all that training, the AI came back with its findings. It zeroed in on the most important ingredients in that disaster recipe. Things like elevation, how steep the slope is, of course rainfall levels, but also stuff like soil moisture and even how rugged the terrain is. These were the factors that it found were most strongly correlated with landslides happening in Nepal. And this is the result. This is the big payoff. The first ever national-scale landslide susceptibility map for Nepal. You can see it right there. It color codes the whole country from the safer green areas to the really high-risk red zones. And what it revealed is that the most dangerous, most susceptible areas are all clustered right there in central Nepal. Okay, but a pretty map is one thing. The real question is, how good is it? Well, using a standard statistical validation method, the model scored an 83% accuracy rate. And let me tell you, for a first-of-its-kind project on this massive scale, that is a remarkably strong result. Now for Section 4, a real-world test. Because, an 83% accuracy score is great on paper. But the true brutal test of any predictive model like this is what happens out there, on the ground, in the real world. So back in 2021, a truly devastating and really unexpected flood tore through the Malamchi region of Nepal. It caused an incredible amount of damage, and tragically, a lot of people lost their lives. And as the researcher Siri Zahal pointed out, the source wasn't just a simple flood from rain. No, it was a massive landslide way upstream that had blocked a river and then catastrophically burst. And here is the absolutely crucial, chilling point. When Zahal went back and looked at his map, a map that was created before this disaster ever happened, he found that the model had already painted the exact origin point of that landslide in bright red. It was already flagged as highly susceptible. The model's prediction was tragically, horrifyingly accurate. So let's recap. We've got a model with 83% accuracy that just proved its worth in a devastating real-world tragedy. That sounds like a home run, right? Problem solved? Well, not quite. It's more complicated than that. Which brings us to Section 5, Promise and Pitfalls. Because this, right here, is what separates good science from hype. It's all about being brutally honest about the limitations of your work. In fact, the researcher himself is the first to point out 4 major weaknesses. First, that landslide database he used, it's really incomplete. Think about it. He had maybe 300 data points, when there could be as many as 20,000 landslides in the full record. Second, that impressive 83% accuracy, it's from a single model. It could just be a lucky fluke. Third, some really key variables, like the local geology and soil types, weren't included in the analysis. And finally, the satellite data itself isn't perfect. It can have its own errors and biases. And you know what? This kind of honesty is exactly what makes the science so trustworthy. And that brings us to our final section, the road ahead. Because pointing out all those limitations isn't about admitting defeat. Not at all. It's about creating a blueprint for what to do next to build a much safer, more resilient future. So the plan is actually crystal clear. First, use more advanced AI. We're talking things like convolutional neural networks and super high-res satellite images to automatically find past landslides and build a much, much bigger and better database. Second, you gotta verify the results by testing them against other machine learning models just to make sure that 83% wasn't a fluke. And third, you have to go back and improve the inputs, correcting for any possible biases in things like the rainfall and soil moisture data. Look, this project is an absolutely powerful proof of concept. It shows what's possible. But it also leaves us with a much, much bigger question, one that goes way beyond just Nepal. As our ability to map, monitor, and even predict the Earth's systems grows at this incredible exponential rate, the ultimate challenge is still ahead of us. How do we translate all this amazing new knowledge into action, into policies, into early warning systems, and into infrastructure that actually saves lives on the ground?